3 minutes.
I know for me it's better to press the button now because I mean I cannot be 100% sure in my connection.
I see.
Hello.
Hello.
Здравствуйте. Hello.
And hello, everyone, especially hello, Gregory.
Hi, Philip.
Hi.
Some trouble with camera.
Aha.
Well, you can see me anyway.
Wow.
Ира Ярославовна, здрасте.
Oh, здравствуйте. How many percent of people understand how to talk? Maybe just
13 people.
yes. No,
Yeah, we still have
Alexei,
5
you,
minutes.
Greg, also, I hope so. Yes, still. Витя, привет.
Anomaly.
Привет, Ярослав.
Привет.
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 Привет,
У
Витя.
меня не работает камера, поэтому меня не видно, но,
Да, ну слышно. Привет,
но
Виктор.
слышно, по крайней мере.
Да, привет.
О. Ричард, добрый день.
Добрый день. Кто тут у нас еще?
Гриша, привет.
Виктор Александрович, это вы или кто-то
Это
другой?
я, но без
Я очень
видео.
рад вас слышать, но не вижу.
Взаимно.
Gregory, by the way, is it okay if people ask questions during your talk, or do you
Yes,
prefer at the end?
that's perfectly fine. In fact, I was
Okay.
going to suggest that because this is a little technical, so I was going to go through details.
Okay,
So I'm happy to clarify if something is not on my slides.
Okay, great.
In fact, there is some echo, maybe only in my computer. What do you think? Alexei Koshelyev, do you have some kind of echo?
I had, but now it looks like okay.
Yeah, now it's fine.
Shall we start now or we can wait? We still have 2 minutes.
Yeah, we still have at least 2 minutes.
At least 2 minutes. About 30 people. Okay, maybe we can start now. Okay, hello everybody. Today we have a pleasure to have a talk by Greg Gabadadze. He will tell us about new gravitational action for trace anomalies. Please, Grisha, 1 hour.
Yeah, thank you very much, Irina. Luca, thank you very much for the invitation. It's a pleasure to give this talk to this audience, although I don't see most of you. Please feel free to ask questions. I may have a hard time to follow the chat if too many questions come through chat, but I hope the organizer, perhaps Luca, can stop me in appropriate place and ask me that question. So that's how we'll go. So this talk is about a new gravitational action for the trace anomaly. So I mean anomaly in the trace of a energy momentum tensor, of a field theory, or quantum field theory of some matter fields, conventional matter fields. This is based on a preprint on the archive, which I put a couple of weeks ago, maybe 3 weeks ago. So you all are familiar with anomalies in quantum field theory, such as axial anomaly or scale anomaly, which obviously is a quantum effect. So those anomalies don't necessarily appear in the action that or the Lagrangian that we write down, the classical Lagrangian, which we subsequently quantize. So we will have to go after that and calculate some loops through which we learn about the anomalies. But there is also an approach which is well known, in which you ask the following question: can I write down an effective Lagrangian to be defined more precisely as to what effective Lagrangian it is, such that variational principle applied to that effective Lagrangian would capture the anomaly equation already at that classical level. And that's the approach I will be discussing for the trace anomaly, for gravitational field trace anomaly. Before I go to a gravitational theory, I just want to give you a toy example, which is a well-known example. There is nothing new here, but I want to emphasize certain aspects of this toy example, which are precisely relevant to the point that I've just made. So this will be conversation about the axial anomaly. It's different from trace anomaly. Nevertheless, it's an anomaly. The axial anomaly in 1+1 dimensional massless electrodynamics. That's what's called massless Schwinger model, as you know. And what I will discuss in the next 2 pages that you see is how that quantum anomaly, which we know emerges through one loop diagram, is in the end encoded in a Lagrangian. Now, in this case, that Lagrangian is actually the exact Lagrangian because the Schwinger model is exactly solvable. Nevertheless, you can think of this as an analogy of an effective Lagrangian, variation of which would give you the anomaly. So let me begin step by step. As I said, Schwinger model. Luca, do you see my pointer? Yeah, good. So the Lagrangian is just -1/4 f mu nu squared plus the massless Dirac fermion field coupled to that gauge field. That's an abelian gauge field for simplicity. The signature that I chose from this theory is plus minus, and then mu and nu are 0 and 1. And it's easy to figure out that the coupling constant, which is called E here, is dimension full. Simply from the Maxwell term, you see that the gauge field has to be dimensionless. And then from the fermion kinetic term, you see that the fermion field has to have dimensionality 1/2 of mass. And if so, then E ends up having dimensionality of mass. So this is obviously well known, and that dimension full coupling constant is responsible for many things in this theory. In particular, the fact that it's super normalizable, but also the fact that it has a mass gap, as will be seen from this Lagrangian, effective Lagrangian description. So 2 symmetries are of relevance here, the global symmetries, the vector symmetry U1 vector This is just the conventional phase rotation of the fermion field. That's a symmetry, as you know, that is responsible for the conservation of the vector current. And then you have also the axial U1, which is just e to the I alpha gamma 5 rotation of the fermion field. Again, this is a global symmetry. So a classical Lagrangian is invariant under both. But then, as you know, when you go into the analysis of the quantum theory, you cannot preserve both at the same time. There is a fundamental clash between the two. And we choose to devise our normalization procedure or our quantum procedure so that the vector current is conserved. And axial current then acquires the anomaly, which is written down here. So the derivative of the axial current is the charge, dimension for charge divided by 2 pi times the epsilon tensor. This is just an antisymmetric Levi-Civita tensor in 1+1 times the field strengths. And that all comes from this one loop diagram. A wavy line denotes the external photon field or gauge field. And the cross here is the insertion of the axial vector. Which is also related to the polarization diagram in this theory, because there is a simple connection between gamma mu and gamma alpha times gamma 5 via the epsilon tensor. That's the nature of this 1+1 dimensional algebra. So let me then talk about that Lagrangian out of which I want to get this as classical effect. So for that, you can use bosonization, and there are well-defined strict procedure for doing bosonization. Coleman did that in the context of relativistic field theories, but I think it was done even before in other contexts. But in any case, here is a short version of it. So the vector current can be represented after taking into consideration equations of motion, actually, can be represented as the epsilon tensor times derivative of a certain scalar phi. And as you can see in this representation, it's automatically conserved because this already took into account some equations of motion. This is not the most general representation of a vector current here. It already used equations of motion. But axial current then follows. It follows that the axial current will be represented as just 1 over square root of pi times d mu phi, because of the connection between the gamma matrices that I mentioned, that gamma mu gamma 5 is proportional to epsilon mu alpha times gamma alpha, and that's the connection between these two vectors. So now I'm going to take these expressions and plug them into the equations of motion that follow from the initial classical Lagrangian. So this is the Maxwell equation, d mu f mu nu equals to, it should be charge times the electric current, which now is represented through this. So that's what's written in this equation.
I'm sorry?
Yes?
What happens?
Is there a question?
No, it's okay. Sorry.
Oh, okay. So this is just the Maxwell equation rewritten in terms of this phi. And the second equation is the anomaly equation. It's literally what I had on the previous page, d mu j mu 5 equals to the right-hand side, and now d mu j mu 5 are replaced by this expression of j mu 5. So you'll get box of phi equals to the right-hand side. And as you see in these two expressions, there are no fermion fields anymore. You only have a vector field and a scalar field. So then the question is, can one write a Lagrangian such that variation of that Lagrangian with respect to these two bosonic fields will give rise to these equations? And the answer is yes. This is the Lagrangian. It's a very simple exercise. Again, you have the Maxwell term. That term reproduces for you this. And then you have a mixing term between the phi and the epsilon tensor times f, which you can think of as f dual in 1+1. That's a mixing term. It's an important term to give you precisely the right-hand sides in those two classical equations. And then you have a kinetic term for the scalar. So here it's a proper sign kinetic term because I chose the signature, which is plus and minus. So the proper sign kinetic term is plus, and in the gravity part, I will have the opposite convention for convenience, but here it's a proper scalar. Now, that achieves the goal. So this is the Lagrangian, which you can just vary and get the anomaly equation so that quantum effect is already encoded. Not only that, but it also encodes lots of physics of the initial quantum theory. If we go back, you know that vector field in 1+1 has no propagating degrees of freedom. You can think of that in various ways, such as that A0 has no kinetic term and A1 can be gauged the way through, gauge fixing. Therefore, if there is anything that should be coming from the fermions, so you can be thinking of this effective Lagrangian as having fermions integrated out, but keeping, of course, when I say out, we keep their quantum loop contribution, which is exactly the same loop that contributes to the anomaly. And that gives you this scalar kind of bound state of those fermions, which you can prove that it's massive. It's not immediately obvious from this Lagrangian, the bosonized Lagrangian, but I'll give you a hint. Let's say you can go to A0 equals 0 gauge, in which case these two terms simplify, and you can complete this to a full complete square. The quadratic term that you will have to add to that will be just mass term for this phi. But the complete square itself will be just the Gauss's law. So it vanishes on the Gauss's law modulo integration constant. So that's gone on physical states, and then you will just have the massive scalar. That's it. The mass is E squared, the mass square is E squared over pi. So this is all well-known results. So just to summarize this is a toy example in which you achieve the goal of having quantum axial anomaly captured by some Lagrangian, which you just vary with respect to the fields, and you get the anomaly equation. So we'd like to do the same for gravity. Why would you want to do that for gravity? Well, the reason is clear. There are physical effects associated with the trace anomaly in gravity, either, well, you can choose to go ahead and do loop calculations every single time, or quantum calculation, quantum corrections every single time. But it might be more convenient if you had an effective Lagrangian in which you already encode those quantum effects, and you would extract them through variational principle, and then solving those, more complicated equations, of course. And that's the philosophy here. So a brief review. I'm going to go through a very brief review of the trace anomaly and how it shows up in with gravitational field, and then the prior history about this such an effective Lagrangian. Some comments about the literature, which is subtle and intricate, and then I'll go to the new proposal. Well, I'll discuss also the problems of the status quo, and then I'll discuss a proposed solution for those problems. So we are now in 4 dimensions, and we no longer are talking about axial anomaly. We are talking about the anomaly in the trace of the energy momentum tensor of a quantum field theory. If I have a simple theory, such as, let's say fermions and a gauge boson, or alike, with no mass scale, you can just derive energy momentum tensor through usual methodology, and then at the quantum level, you will get this anomaly that the trace is not 0. Classically, it was 0 because it has no scale, theory has no scale, but quantum mechanically no longer 0, it equals to some coefficient multiplying the field strengths here. This was first noticed in these 2 papers, but at the level of the word identities, this equation that I'm writing here was emphasized, I think, a little bit later as a Heisenberg equation. These are relations between Heisenberg operators in quantum field theory. But that relation gives rise to all the other word identities once you sandwich this operator between different states. And as I said, mu and nu are 0, 1, 2, 3. And now I'm going to be using mostly plus signature. So far there was no gravity, and now my main focus will be on gravitational field. I've got to tell you that this effect, the gauge part of the trace anomaly, is trivial to incorporate in the effective action that I'll be discussing. And because of that, I won't be carrying it around. Maybe at last stage, I will tell you how the term appears. It's really, there is no controversy about that. That's trivial. But I will worry about all the gravitational parts. So once you introduce the gravitational field, here is the analog of this trace anomaly. So what stands on the left-hand side is the expectation value of the Heisenberg operator of T mu nu. So that's calculated. You should think of a partition function with path integral. So in path integral, you are integrating with respect to all the matter fields, but you're not integrating with respect to gravity. It's sufficient for these purposes to keep gravity classical, actually, even though you can quantize gravity as an effective field theory as well. That will be additional little complication, technical one, but and not necessary here for the points that I'm making. So because of that, what I just said is the simplest approach. So that's the expectation value of this T mu, and it equals to, in a conformal theory, it equals to some coefficient times, this is Euler invariant, times another coefficient times the Weil tensor square. This is a Weil tensor. I didn't put indices, but well, it's squared of that, and it's defined down here. And then there is also this term. And as you can see, I kind of crossed it out. The reason why is because, again, this is, first of all, it's arbitrary, because this coefficient is arbitrary in the effective Lagrangian that I'll be talking about. And it's easy to incorporate. You just add the R squared term to the effective Lagrangian. The variation of that R squared term, appropriate variation, gives you this term. So because of that, again, I'm not going to be carrying this around for simplicity of the equations, but in the final answer, you can always include this, like the gauge anomaly. So I'll be focusing on these terms, although you will see that the Weil square is also very simple to incorporate for the same reasons, but it's good to keep track of the relationship between the two. So the Euler invariant here is, R mu nu square, Riemann square minus 4 times Ricci tensor square plus R square, and this Weil square, as I said. And at the level of the correlation functions, this was first derived by Kapper and Duff, and then with subsequent developments by multiple authors, solidifying all the knowledge about this relationship. So now, if you're thinking of a gravitational field and you did variation with respect to the metric and took the trace of it, you know that the m Planck square times R, the Ricci scalar, should equal to the trace of the energy momentum tensor of the quantum or of the fields that you couple to gravity. And since I was assuming here the simplest case in which those fields were conformal, just for simplicity, then the anomaly would modify the trace equation, like the right-hand side of the trace equation, to be just this expression. And you should be thinking that there are other terms here, of course. So in realistic standard model, there are terms which explicitly break scale invariance, such as all the masses, and so on and so forth. You can, those have nothing to do with quantization. They are in the classical theory. Those just are implied in this expression, if you need to include them. Now, so the goal is to derive an effective action which has a variation at which has one of the equations of motion. That's the goal, like we did in the Schwinger model. All right. So the Riegert was one of the first ones to ask that question and try to construct that action. And very often in the literature, you will encounter that it's called the Riegert action, and I will continue to call that. Although I should say that whenever we cite Riegert, we should cite Fradkin and Zeitlin, because this paper is essentially simultaneous, and this is Efim Fradkin, not to be confused with Eduardo Fradkin. This is Efim Fradkin. So at the same time, essentially in the same, I think in the same journal. There is a slight difference between the two in terms of the approach and generality. I would say that the Rigert's is a little more general, but the answer is the same. So I will come to that answer, but I just want to make that comment about the literature. So the goal is to find some action S sub A stands for anomaly, which is a functional of the metric and derivatives of metric, which I'm not writing here for simplicity, such that the trace of the variation would give you the right-hand side of this Einstein equation, and that's A times E plus C times W squared. And then, well, it's obvious why this is good. Then if you combine this SA tilde with the GR action, general relativity action, Einstein-Hilbert action, that's going to give you precisely this equation, because the Einstein-Hilbert variation will give you this, the left-hand side, and then variation of this additional piece gives you the right-hand side, and you accomplished your goal. So in that paper, Rieger actually argued that if you impose a condition that for this SA tilde to be to depend only on the metric field, then you cannot write it as a local functional. But he also pointed out that if you manage to, well, not manage, if you introduce essentially additional degree of freedom or additional field at this point, let me call it, in the following way, then you can write it in a local representation. So the metric is here with lower indices is e to the 2 sigma times G bar. So that's a connection that I will be using a lot. So one is a conformal or wild transformation of the other. And as you know, in general relativity, this is entirely ambiguous because you can shift sigma and you can conformally rotate G bar so that you can make sigma go away, which is essentially the gauge choice for that symmetry, but not after you wrote this Riegert action. So here is the form it takes that Riegert derived. So the total action is the GR action, conventional Einstein-Hilbert action, in which instead of G, conventional metric, everywhere you substitute this expression. That will be the Einstein-Hilbert action in the Jordan frame, if you will. Well, this is just the formality at this point. And then the Riegert derived this additional piece, and so did Fradkin and Zeitlin, I should say. This additional piece, which depends on G bar and sigma, but not this conformal invariant combination separately. So, and moreover, this S sub A has a very specific form. If you look at it, naively, it's a scary expression, but actually it's a very special expression. The first term is sigma times the Euler invariant, Euler density. And second term is the contraction of the Einstein tensor. This G capital is the Einstein tensor here, contracted with derivatives of the sigma field. The third term is what is now called the cubic Galileon. Back then, that name was not used, but now it is being used. This is called the cubic Galileon. And the last one is what's called the quartic Galileon, but they combine into what's called a conformal Galileon, actually, in modern parlance. And then that's the A term, and then there is a C term, which is the reflection of the while anomaly, and I see that I missed here sigma. There should be sigma here. There is a typo. Sigma is missing, so sigma should be multiplying this W bar squared. So the Riegert's point was that now you take this action and you vary with respect to sigma, and then once you perform the variation, you express back G bar in terms of G. so that you get an equation which is written only in terms of G, and that equation exactly the trace anomaly equation. So this way, Rigert accomplished the goal. But there are a few comments that I'll make. First of all, this will be, I will argue that this is a problematic theory. Actually, it's as an effective field theory, it gives rise to lots of problems, as I will argue on next page. But before I even go there, again, comments on the literature. Rigert derived this with the assumption that the G bar had fixed determinant. Then because of that, he thought or perceived this as a non-covariant action, because you see it all depends on G bar. Fratkin and Zeitling derived that even under more restrictive condition that G bar is actually Ricci flat. I'm sorry, it's just, yeah, Ricci scalar equal of G bar equals to 0 under that condition. And then what Rigert did after that was to re-express sigma in terms of G, in terms of some non-local operators, because he perceived this as a non-covariant action. But and that's how that's how it was regarded for a very long time, until the paper of Komargovsky and Schwimmer. Although they had very different emphasis, they were talking about the proof of A theorem, which they did, but this is the same action which appears in the Komargovsky and Schwimmer paper on the proof of the A theorem, in which they derived it from other principles. The principles being that this gives you variation of, it gives you the Weil anomaly exactly, and that put this really on a solid ground. And makes you think of a very simple argument as to Rigert's initial action is covariant. It can be covariantized in a very simple way. You just write it down and you just declare that G bar is not constrained at all. You can have transformations, the scale transformation G bar, and if you want to fix those transformations, sure, you can fix those transformations. Then you get you get the approach that Rigert adopted, but you don't have to. So it is actually, as it is written, this is a fully covariant action with the metric tensor and the scalar transforming according to the tensor transformation and the scalar transformation of general relativity. And it's consistent with obviously what Komargovsky and Schwimmer did. Moreover, in an independent study with my former student, Georgi Tukhashvili, who is now at Princeton, we derived this action as a coset. If you ask the following question, let me start with some conformal invariant theory in which I assume that the conformal invariance is spontaneously broken down to the Poincaré invariance. And we know all the machinery, how to construct those kind of theories as a coset. So it's a coset of SO2, 4, or the conformal group, or the Poincaré in 4 dimensions, ISO 1, 3. That construction exactly leads to this formula as a Vezumino term. You just construct conventional effective Lagrangian terms, and then there is one more, which can be represented as actually 5-dimensional term, and it's pullback on 4-dimensional boundary, and that's what the pullback is. It's just a Vezumino term in that construction. So these arguments obviously put this Rigert action or Rigert-Fratkin action on a more solid footing in terms of it being as it is and very general, and the action for the trace anomaly indeed. Okay, so after that digression to literature, let me now tell you why this theory, the action which is written here, is problematic. The general relativity plus the Rigert action.
Sorry, Gregory, can I ask a question?
Yes, please.
So, for instance, if we go also for gravity here in 2 dimension, in that case, the trace anomaly would be just T mu proportional to Ricci scalar. And in that case, we know that there is the Polyakov action from which we can derive the trace anomaly in 2 dimension. And the action contains this 1 over box, so basically it's not local. If you apply now what you have just shown, this Rigert-Flaherty-Teichling method, which seems to be still kind of local because the action is local, and you apply it to the two-dimensional case, would you get, I mean, would the two procedures be equivalent, or
Yeah,
would
yes.
be totally different?
Yeah, so they are equivalent. They're exactly equivalent. You can do, as I said, you can also do coset construction in 1+1 and you get that term. So let me make a comment about a little bit about terminology. The Polyakov action, I don't regard it as a non-local action. Anything, you can write it R times 1 over box times R, but that you can always represent as R times phi minus kinetic term for phi.
Sure.
So anything that you can rewrite as an action with finite number of degrees of freedom and local terms, that I call local action.
Okay, so in this sense, they're completely equivalent.
Exactly. In that sense, they are completely equivalent. Yes. Thank you for that question. Yes.
Okay, and for instance, if you would, I mean, if you would try to just rewrite this action in some, let's say, 1 over box form, do you know what, how would it look like? Or?
It's a difficult task because to do that, you would have to integrate out the sigma field. So once you write down the equations of motion, sure, in the trace equation, in the trace equation, sigma field disappears entirely. That's a very special nature of this action, as it should, because it should give you the anomaly equation in terms of G without any sigma.
Yeah, sure.
But there is T mu nu equation, and so that has sigma in it. And it's a highly nonlinear equation because you have these Galilean terms here, and you cannot that easily resolve the sigma field from that equation. I mean, you can resolve order by order in nonlinearities in non-locality, and sure, you can write that. In fact, that has something to do with this initial point that this action is not local precisely. But
yeah, because it would be nice to get some like final local, let's say, expression where you only have curvature invariants, because in that case, maybe it's easier to see the covariance of the final action then, right?
Well, covariance is straightforward here, local, right? So this is so you have this term has two fields in it. One is a tensor, G bar, and another one is sigma. So let's do diffeomorphisms, conventional diffeomorphisms. So this is invariant under conventional diffeomorphisms of G bar.
Okay.
So there is no issue with that. It's straightforward. Now, sure, you may desire for certain reasons to rewrite this, to integrate out sigma, and express everything in terms of invariance of G bar. That's a difficult proposition. It's not as easy as in the Polyakov action, in which the integral is Gaussian. Here is you have quartic terms.
No, I see.
So
okay. Okay, thanks. No, I see.
Okay, so let me. I see there are something in chat, but I'm not checking that. I apologize because I.
No, I think it was just a question. What is sigma? But it was answered already in the chat. Like it's just an opposite. Yeah.
Got it. Okay. I'll check those questions by the end. So now the issue, why that is a problem, even though that derives what we want, I'm saying there is a problem. And why there is a problem. And by the way, this problem was pointed out in a very different context. I should have cited here by Kurt Hinterbichler and Bonifacio and Laura, I think. But my paper has a citation, so they were to point out this problem in a different context. But it applies exactly in this context. So you take this action. So as I showed you, in SA you have lots of nonlinear terms for sigma, and you can just redefine field back to normal, the Einstein frame. So you're gonna have GR action in terms of this Einstein-Hilbert action in terms of the metric. And then you can redefine here. Now, this should be SA bar. The form of this is very similar to this, but coefficients are different. So hence, I should have distinguished it. Should be different. It's not identical. There's different coefficients. Should be bar. But the essence doesn't change. This one still has Einstein tensor times derivatives of sigma. There is the cubic Galilean term, and then there is a quartic Galilean term in it. So now you've got a theory in which there is no kinetic term for sigma anymore, because this is just the GR action. There is no sigma in it, in that basis. Yet you have high nonlinear terms. So such theories don't make actually sense as effective low energy theories for multiple reasons, but let me talk about the very basic one. So imagine you had a theory in which, there is a fourth derivative, the derivative of sigma to the fourth power. And you now introduce small kinetic term to regularize, to be able to write propagators and develop some, scattering problem conversation or for any other reasons. And then you can rescale the kinetic term so that this scale, this z, goes into the denominator of your higher dimensional term. This would be the canonically normalized field. But z goes to zero limit is the one that we have in this theory, which there is no kinetic term, corresponds to this term blowing up at arbitrarily low scale. So for instance, the scattering amplitude for the sigma, which is a 4-point amplitude, which would behave as the Mandelstam invariant square divided by z to the fourth, will blow up for arbitrarily low energy scales. So because of that, it's not a meaningful theory. Moreover, this was conversation about flat space, about Minkowski space. I mean, you can think of some background, some gravitational background. Let's say you solve equation of motion, you get some backgrounds. Well, this G mu nu will have some non-zero value. And then if you look at those fluctuations about the G mu nu, this will give you some quadratic term, some kinetic term sigma. But its sign is completely determined by the background. So you can get plus sign, you can get minus sign. So in one case, you will have a ghost, in the other case, you will have some sort of scalar. And you cannot have a theory in which, healthiness of your fluctuations depends on what background you chose. And I'm talking about very low energy backgrounds. I'm not talking about anything close to Planck scale or anything like this. So it is clear that this theory cannot be theory of our nature, gravitational theory of our nature. Well, GR is, now you want to incorporate anomaly. Well, you incorporate anomaly through the trigger term, and then that theory doesn't make sense. So you have two options, either to cancel that anomaly, that's one option. If you come up with a theory in which, well, there are such theories, of course, in which trace anomaly equals to zero because it's some additional fields that give rise to cancellation, then there is no conversation that we're having here. You stay within general relativity. But if that's not the case, if the trace anomaly is not canceled, then the resulting theory is infinitely strongly coupled and hence needs to be modified. Now, how to modify, to answer that question, let me go to the root cause of the problem. And the problem is in some ways simple. The Rigert action essentially introduced some nonlinear derivative terms for sigma. But sigma itself is not a dynamical field in general relativity. So conformal mode is not a propagating degree of freedom in general relativity. So to see that, there are many ways to see that, but this is the most instructive one in the context of what I'm going to propose. Let's look at the small fluctuations around flat space. This is a standard, it's ADM decomposition essentially with some notational differences. So let me denote H00 as 2 times n, and then H0j will be the transverse vector times a gradient of a scalar, and then Hij decomposes into transverse traceless tensor, and then transverse vector plus 2 scalars, which is one comes with derivatives, another one without. The one that comes with derivative is a gauge mode, and one without the derivative is the conformal mode actually. So in this language, really propagating degrees of freedom in general relativity are these Tij transverse traceless. That's the only propagating degree of freedom. Anything else is either gauge removable or is constrained by GR itself. And this is what I want to show you or remind you. This is well known, of course. This is a textbook subject. that in, let's say I choose a gauge in which rho equals 0, u equals 0, which is straightforward, then what you get for tau, for the conformal mode, is this expression, in which n acts as a Lagrange multiplier. So the moment you take variation with respect to n, that gives you Laplacian of tau equals to 0. If you assume conventional boundary conditions, then this tells you that tau cannot depend on spatial part. So you only get here, for tau, you only get time dependence and time derivatives. It's only a homogeneous mode. Well, actually, this mode is the FLRW cosmology. That's what we do in FLRW cosmology. We use only homogeneous mode, and then we look at the fluctuations. But this tau by itself is not a physical propagating degree of freedom like the transverse traceless modes of the graviton are. So those are just, plus minus 2 helicity states of massless graviton. This is not like that. So what happened here is that this mode was not propagating in the Minkowski space, right? And the Rig reduction introduced additional higher derivative terms. I should say, which I forgot to emphasize, that even though this Rig reduction has those higher dimensional terms, the equations, they are so special that the equations of motion are still second order, as you know. When I was talking about Galileans, that's the defining nature of those Galileans. And this whole thing goes under the subset of the theories that were derived by Hortensky long ago in the mid-1970s, asking a question, what's the most general field theory of a tensor and a scalar, which has still second order equation of motions. The Cauchy problem is well posed. This is part of it. Now,
sorry, Gregory, there is a question from Alex.
yes. Hi, Alex, go ahead.
Hi, Gigas, great talk. I'm just puzzling because I'm puzzled, sorry, because this action, it's subpart related to sigma. It's of course a Hordensky story, but the coupling to Weil and this Euler invariant, it's not in Hordensky. It's beyond Hordensky.
Yeah, but this is a kind of trivial part in a way that you see. The reason why this is a Weil density is because if you didn't write here sigma, it's a total derivative. Right. So that's a reason why you get Euler characteristics for manifolds measured by this. Sure. So that same property plays the role that you get second order equation of motion, even this term from this term too.
Right, but I'm not sure if you vary with respect to the metric this because there's supposed to be sigma in front of Weil, right?
Yeah, you do get that's precisely the reason why you get still second order equation of motion.
But even varying metric in Weil, you get second derivatives of sigma. You mean?
That's right. No more than 2.
Okay,
no
so that's in that sense.
No more than 2 per field. So you total number of derivatives will be more than 2, but no more than 2 will be applied per field.
So basically, the violation happens only if you vary the metric, but that's your probably next step.
No, I mean, with respect to what I'm saying is that just if you take the Rig action and vary with respect to either sigma or the metric, you always get equations of motion in which there is no more than 2 derivatives acting per field.
But per sigma field, per metric,
per both fields.
Really?
Both fields. Yes.
Okay, then I'm puzzled. Okay, let's postpone it. But okay, very interesting.
Well, that's easy to see precisely because of this being total derivative actually.
Yeah, that's true. But with Weil, this would not go.
Oh, with Weil, you mean this?
Yeah.
Oh, this we're talking about. Oh, this term.
Because this Euler is Gauss-Bonnet, right? That's
right. Euler, I'm sorry, I was focusing on this term. Now, this term, yes. This term I cannot remember actually. This term I cannot remember. It may give you 4, but but this is not so this term will be in the end among the ones which will be suppressed by higher scale and not important indeed, as you were saying. Yes.
Okay.
As you will see. Yeah.
Great. Thank you.
Isn't that term missing a sigma?
Yes, it is missing a sigma. As I before I mentioned that I noticed that I left out sigma here. Should be sigma. Yeah.
Right.
Yeah, yes, I was calling the Rig reduction this one. This is the one I'm focusing on. Yeah. So okay. So now the proposal is this. So somehow we need to introduce the kinetic term for the conformal mode already at the free level. And if you do that, and then incorporate quantization and essentially add the Rig reduction to that, then that problem should go away, the one that I alluded to. Simply because the sigma field will have conventional kinetic term to begin with on flat space. Those higher dimensional terms will be valid up until certain scale, which I'll have to specify what it is. And as long as you stay below that scale, then everything should be fine. So that's the approach. And the proposal is to modify the GR action into the following: the R minus R bar action. The R action is the conventional Einstein-Hilbert term. So this M capital is, you can think of this as being M Planck. It's actually M Planck divided by square root of 2, or simply just M. But the other term is also Einstein-Hilbert term. The difference is that it's got minus sign in front. It's very important, minus sign. And it is written in terms of this G bar metric, although nothing precludes you to rewrite this whole thing in terms of the G metric, because you still have this connection. So point I would like to make is that this is still a theory of one tensor field and one scalar field, which you can rewrite either in terms of G and sigma or in terms of G bar and sigma. Classically, that's equivalent. Now, and I'm going to assume that M bar, this new scale M bar that I'm introducing here by hand, is less than M, maybe significantly less. There will be some physics that will specify how much less this should be, but for now, I don't need more than 2 orders of magnitude, maybe 3, maybe 4, depending on details. So it's still a high scale. I'm still thinking of this M bar as being, for sure above the standard model, above the TV scale. Would be close to the God scale, perhaps, or maybe a little less than that, somewhere in that neighborhood. Okay, so then if you look at this theory and do the same as on the previous slide, so you will get additional pieces in the Lagrangian for the conformal mode. They are proportional to epsilon square here. And then it's very easy to see that the constraint that you had before, which was, Laplacian tau equals 0, now gets modified. So it essentially relates tau to sigma. So formally there are 2 fields, but one combination is non-dynamical. There is another one which is dynamical. You can think that way, but or you can think that you express sigma in terms of tau or vice versa, whichever way you'd like to think. But the point is that once you solve this constraint and substitute back into the Lagrangian, you get a proper kinetic term for either, of course. Let's say for sigma, we're focusing on sigma. For sigma, you get the kinetic term, which is 6 times m bar squared. This sigma square with minus sign. This minus sign is the right one with this metric, with this signature. And then there is 1 minus epsilon square. Now, epsilon square is a small number. You can ignore it. So this is essentially minus 6 times m bar squared d sigma square, which is a healthy kinetic term for that sigma already at the tree level. So therefore, and it's very important to have this minus sign here. Without this minus sign, you won't get it, because as you know, this goes back to a simple observation that in general relativity, conformal mode has is wrong sign kinetic term if we just restrict to it. So this makes it right. And then it for the tensor mode itself, this won't give rise, the minus sign won't give rise to any problems, because you have a bigger kinetic term here for the same tensor. So that's how this works. So here is another I feel like I'm running a little late, so let me go quicker. I'm gonna go a little quicker now. So here is another way of rewriting the same R minus R bar. This is now written in the Einstein frame, everything. In fact, this M bar scale appears as a vacuum expectation value of some field phi. So this is a different field, obviously, from two-dimensional one that I used. And interestingly, this theory has a following symmetry, this transformation, which looks complicated, but actually its origin is very simple. I mean, I can explain that if there are questions. I just don't want to spend time on it. But this symmetry tells you two things. A, if you want to preserve it in the matter sector as well, then matter should couple to this metric, because this is a metric which is invariant under that symmetry transformation. It's a straightforward check, although kind of a little technical. But that metric is approximately G. For practical purposes, it's approximately G because it differs from G by some terms which are epsilon squared. And I'm assuming epsilon to be small and negligible at this point. So that's essentially G. Now, another virtue of the symmetry is that it tells you that certain terms, once you start quantizing, for instance, phi, certain terms won't be generated, such as the mass term for the phi won't be generated and other terms for the phi won't be generated. That is important because this structure is the only one that gives you the right trace anomaly equation. If you shift things around or add some, let's say if I add here phi square term, for instance, that's gonna change my trace anomaly equation when I do variation, irrespective of what I have in the Rieger term. So this is the one that protects. So either you should do this, that's what I'm saying, or you can choose to couple matter to just G, in which case you will induce mass and potential terms for phi through the matter loops, but you can suppress them by choosing low values of M bar. So at this point, before you go to discussion of physics and what the manifestations is, those two options are possible, but I chose the symmetric one in which I postulated G hat being the one to which matter couples, so then the symmetry is present in that coupling too. So there is also a duality, by the way, here, which is that there's a duality between these two sectors, R and R bar. If you replace M with M bar and G to minus G bar and sigma to minus sigma, this whole thing is invariant. Okay, I'm gonna skip slide, page number 10, because what this page does is argues that all the local corrections, which can be generated through matter loops or maybe some heavy stuff that exists above scale M bar, they will be all suppressed at least by 1 over M Planck. There is an argument to make it. It's here. It's also in the paper. I'm going to skip it for the sake of time. And the reason why this is important is that, of course, in the effective Lagrangian in general, you have infinite number of higher dimensional terms. But the point is that all those conventional higher dimensional terms, they'll be suppressed by M Planck, while the Rieger terms will be suppressed by lower scale M bar. And that's why you can keep them in the action, but neglect all the other ones. So here is the action. So the Einstein-Hilbert term in terms of sigma and R bar, the R bar term, and the Rieger term. And here I restored sigma in this term. Now, so the variation with respect to sigma gives you just the trace anomaly equation, the correct one. I should point out that even though all my discussions here were about trace anomaly, this action has appeared before in the literature, which I learned after I put this action on the archive, but it appeared in a very different context. And it's very interesting, actually. Pedro Fernandez, he derived that action from purely classical considerations, asking for equations of motion to be scale invariant, even though the action itself may not be scale invariant. That was a premise of the construction. So you ask, what's the most general theory of a tensor and a scalar in which the action itself may not be scale invariant, but the equations still are. And that leads to this action. So that's a very different logic, very different consideration. It was all classical. It's very interesting. And he also found classical solutions of this. Speaking of classical solutions, I forgot to mention that, for instance, it's very easy to solve for open, for FLRW type cosmologies here. Anything that's conformal to flat, equivalent to flat space, such as FLRW, it goes through straightforwardly because you choose this to be a scale factor times flat, and then this G bar is flat, and that's your FLRW. And this, for sigma, you get equation through which you calculate sigma. It goes through. But Pedro here found general solutions for cosmology as well as for black holes. Very interesting. But my main point here is that GR needs to be modified like this if you want to incorporate the trace anomaly, or else you have to cancel the trace anomaly. And then that entails that there is a new scale, this M bar. Well, there is a new state, new dynamical state sigma, which propagates, and then there is a new scale M bar. Now, the Riegert action, as I will show on next slide, and that will be my last slide and finish, is strongly coupled at that M bar. So that goes back to Alex's question, actually. Anything that's above M bar is not captured by this, and this term will have scale which is above M bar, simply because when you rescale the gravitational field here in the wild tensor square, that will be above. But these terms, the cubic Galilean and quartic Galilean, they will be suppressed by M bar only. So that's a lower scale than Planck. Therefore, those are the only ones you can retain legally. All the other ones you should ignore. They are higher scales, and there are only finite number of them. That's the beauty of it. So you can, whatever exact solutions you get, those solutions are valid within that approximation. So to make it more explicit, what you can do is to take either you can take decoupling limit or simply expand on flat kind of flat G background. And here I've just redefined. I've taken M Planck go to infinity because we're not keeping those M Planck suppressed terms. They are somewhere up there, but we're keeping terms suppressed by lower scale M bar. And I redefined sigma for it to be canonical. And then the Lagrange action that I had on previous slide gives rise to exactly what's known as conformal Galilean. As you see, so this is the kinetic term for pi with a proper sign. And this is a combination of the cubic Galilean and quartic Galilean in exactly the proper proportion, which gives you this as being actually one of the cosset terms of the conformal Galilean construction. So with the coupling to the matter, as I defined, this sigma doesn't couple to matter because of that coupling as I defined at the linearized level. So at the linearized level, there is no fourth issue here. Of course, on some backgrounds, if you go to some physical backgrounds, there will be that coupling generated, and then it's interesting to see what that does. Of course, that coupling is proportional to M bar. This is an unknown scale, and you will have some physics constraining that M bar, but we have not done that yet. So conclusion is that if you'd like to incorporate quantum trace anomaly through this effective action, then this is the action that you should be using. This is the GR action with scale M Planck, and this is the additional action, which is also GR action, but with opposite sign and conformally rescale metric, and then the Riegert action, adding the Riegert action. And it is completely legitimate to retain the higher dimensional terms here because they are suppressed by lower scale than M Planck. And this action gives you the trace anomaly equation. there will be physical consequences because of the presence of the sigma. So there is a new degree of freedom now in your gravitational theory. In addition to the tensor modes, you have now the sigma mode. That's a new degree of freedom. And even though on the flat space there is no linear coupling of that sigma in the way that I coupled it to the matter, there'll be there are no linear couplings, of course, and that means that on the background there'll be linear couplings. And that should be investigated, but those will be small because M bar is much smaller than M Planck. They will be always separated by powers of epsilon. Yet they still might be interesting. And this is the same thing, but rewritten in terms of the other variables, G and sigma, in which case, as I said, Rieger action gets modified a little bit in coefficients, but not in essence. Still, you get those Galilean terms in the Rieger action. So I'll stop here.
Okay, thank you very much for your very interesting talk. Question, please. Okay, Philippe, please ask your question.
Yes. Well, Greg, thank you very much. That's very interesting work. But I think there's a step you still have to take. And that is, you haven't said anything about the coefficients A and C. You've just taken them as outside numbers. But in the trace anomaly, they depend on the matter field content. And if the matter fields aren't coupling to sigma, how could that information ever be fed into the action you're using?
So hi Philip, how are you? Thanks for that question. Yes, you are exactly right. So A and C are precisely so in this expression, A and C are precisely defined by the matter content. You know, sigma itself also can contribute to that, but the matter content will contribute. And they are known in a given theory when you calculate trace anomaly. They are known, as you know. So the way you can think about this Rieger action is that, well, it's related to somewhat to what Luca was asking. You see, if you integrate out sigma, you're going to get here something non-local, which is written in terms of G, because that's the only metric there. So that G, of course, couples to matter, and it knows, how many electrons are running in that loop, which gives rise to this anomaly, and hence it is only natural. So this sigma in the Rieger approach you can think of as kind of auxiliary field which has been integrated in to make it local as opposed to writing in a non-local way. But that's the way how this information about the matter fields propagates into this action.
Oh, good. Oh, very good.
Okay, I see the next question from Sasha Wigman. Alexander, please ask your question.
Giga, have you considered bounds from Cherenkov radiation? Because this effective degree of freedom will propagate even in cosmology or whatever gravitational background, except of probably black holes. It's different from one.
Yes, that's a good question. It will indeed, but there will be some bounds on M bar. But there will be somewhat weak bounds given the huge parameter space for M bar that we have about TV scale, for instance, right? The reason why, that's why it's important to have precisely the tree-level kinetic term for sigma, wherever it was. I can put it. So this term is absolutely important. As you see, if you take M bar goes to 0, which is the GR coupled to Rieger, then you are in trouble because of this term precisely. So, but once you have this term, which is coefficient 1, all of this will give you small correction to that kinetic term on the background, as you are pointing out, indeed. Some of those backgrounds may change the light cone, depending what the background is, but those will be small changes governed by the scale, your physical scales divided by M Planck times M bar, right? So there'll be constraints precisely as you are pointing out, but they should be relatively weak given that this is a very high scale. Think of this as a I don't know 10 to the 12 GeV or something.
Interesting, interesting. And also, of course, the gravitational waves will propagate with a speed
Yes.
different from one.
Exactly.
That's maybe tougher in that case.
Well, that scale is even higher. You see, this also goes to your previous question. From this term, for instance, yes, you will have mixing on a background, you will have a mixing of gravitational wave to sigma, but this term will have additional M-Planck suppression. It's more suppressed than these ones, because these ones are suppressed only by M bar. This is a combination of M-Planck and M bar. Morally, you cannot even keep them in that kind of analysis because they are higher. They go above the kind of strong coupling scale of this theory. So yeah.
Interesting.
But yeah.
Yeah. Also, black holes probably would source this sigma in that case, and this sigma would have a hair around black holes.
Actually, the paper that I mentioned, Pedro Fernandez, he does have remarkably black hole solution. It's a very interesting solution. So yeah, yes, well, there is a I think 2 or 3 solutions that he's presenting, and one, if I'm not mistaken, does have here, but have not gone through details of those. Those are very interesting solutions, definitely.
Okay.
We're looking at them from different perspective, and from perspective again, the trace anomaly and so on and so forth. And yes.
Oh, that's cool. That's cool. Thanks. Very interesting stuff.
More questions? I see a question from Luca. Luca, please ask your question.
Thanks very much for your talk, Gregory. It was very nice, very interesting.
Thank you, Luca.
So I have 2 questions. The first is just to understand if I really understood the logic. So for instance, if we take just standard GR with the matter, of course, as you said, we have this trace anomaly. And the question I try to answer is that, can we find an action whose variation, whose classical field equation would give us this trace anomaly equation? Okay. And then now it seems that the answer is that the only way to do it consistently is to add a new degrees of freedom, is sigma, for instance, that was not there from the beginning when we were computing this trace anomaly. Is that correct?
I would give some qualification to that. That's an important question. You see, conformal, as I mentioned, went through details. You see, conformal mode is in GR, but it's not a propagating degree of freedom.
Sure, it just constrained.
Right. So then what happens is that the moment you start talking about anomaly, it gives to that conformal mode some higher derivative, higher dimensional terms. And that's a source of the problem, because you didn't have proper propagator for that mode, and all of a sudden now you're getting nonlinear terms. So there are 2 problems, as I was pointing out. Either they are infinitely strongly coupled, or if you go into a background, you do get kinetic terms, but then you can have ghosts depending on the background, right? So what this theory does is that makes that conformal mode propagating already at the tree level.
This way somehow is like going beyond GR. Where
Oh yeah, for sure. Yeah,
sure.
Yeah.
So
if I didn't make that clear, I should definitely is going beyond GR, because
yeah, that's what I'm saying. Like to really derive this field equation.
Yes.
I mean, this trace now you need to go beyond GR. That's your point.
That's exactly right.
Okay.
You have to have additional physical statement that you have to have additional degree of freedom, this sigma, which another statement is that which has in it its own physical scale, the new physical scale, this M bar. So at that M bar, the sigma goes strong, but below M bar, you can do calculations reliably, but it's there and it can have physical consequences. Yes.
And indeed, the second question is related to this M bar, actually to this epsilon, because as you said, as long as epsilon is very small, you wouldn't see the effect of, for instance, this ghost tensor field, right? That you would have in this R bar action. But in principle, if epsilon is not that small, you would see this effect of the spin 2 part, let's say, as a modification of the G Newton constant, right? Because somehow we are affecting G Newton.
Yeah, that really depends on how I couple to the matter. So that's why I pointed out 2 versions of the coupling. You see, if I couple through this G hat, then I don't see that. I need to go to nonlinear level. and this coupling is motivated by preserving the symmetry even in the matter coupling.
Mhm.
Now you may say, well, I can adopt different principle. This is not, well, this principle can only come up with some fundamental theory from which this might be derived, right? Maybe that fundamental theory is telling you that this symmetry should be broken by coupling to matter. Well, in which case you would couple to just G. So difference is epsilon squared, but now you're saying epsilon, let's take epsilon, which is close to 1. And if you do that, indeed, then this sigma will couple to the trace of stress tensor, giving you gravity competing fifth force.
Yeah. Okay.
Now that fifth force, you can do the calculation. That fifth force will be suppressed as compared to conventional gravitational strengths by 1 power of epsilon, not by 2. There is there are some rescalings that you can do. You can convince yourself on that. So that means that epsilon in that context has to be small because this is like Brand-Dicke scalar coupled to trace fifth force has to be 10 to the minus 5 or less. So of order 1 epsilon, this will be, if you adopt that route, it will be ruled out, with the caveat that in the same theory, once you go with this coupling, which breaks the symmetry, in the same theory, you'll be generating through loops the mass term for the sigma and the potential term for the sigma. You have additional constraints. You got to keep them low as well, because otherwise they are modifying the trace anomaly equation.
I see.
So there is kind of collective constraints in that approach, in the one in which you would like to see that sigma coupled at the linearized level. So that's the reason. I mean, that's a legitimate approach. One can investigate this. There is interesting physics will be entering, but I pursued this more symmetric one because it's simpler to tell the truth at this point, and it's based on symmetry principles.
I see. Thanks. Now, because in principle, would be, since you have anyway some extra spin-2 field, would be interesting to see whether one can get some non-pathological implications, let's say, from this spin-2. Yeah.
Spin-2, I'm sorry, Luca, I mean, there is no extra spin-2 here, right? So it's the same, spin-2 is the same as in GR.
Sure. I mean, you have this extra term where you have this, let's say, small epsilon, which will not affect the sign of the kinetic term of your spin-2.
You mean the rescale to the constant? Yes. So, but that aspect depends how I couple to matter.
No, I understand that.
All right.
Okay. Thank you.
Okay. Well, I see one more questions from Hong Wu. Please ask your question. Hong Wu, maybe.
Yeah.
Okay.
Okay. In this talk, this duality m to m bar, g to g bar, minus g bar, and sigma to minus sigma. What kind of duality, and why duality sigma to minus sigma bar is the one dimension?
Yes. So there is this duality indeed. What it does, it exchanges these two terms to one another. In fact, very interesting that you can, once you add the Rieger term, that duality also changes to Rieger term to itself in a different frame. So it goes through in a full theory. Moreover, you can also couple when you couple to you can write down the coupling to the meta fields through this G hat, and that duality can be made exact there too. I worked it out in a paper. It's written there, so it's there. Now I was trying to use this for avoiding some other fine tuning, such as cosmological constant and so on and so forth, which is a big deal, but it doesn't, because you can still add terms which would be like cosmological constant times some polynomial of phi, which are invariant under this. So it doesn't protect. I didn't find good application of it, to tell the truth, but it's curious that it's there, and I feel like it's interesting.
Okay, more questions? I have a couple of questions. Why very simple, maybe very some. What happens when omega goes to 1? Because you get here a pole. What do you think?
Yes.
Or you have some restriction?
Yes, there is a restriction which I didn't write, which is omega is hyperbolic tangents of a general parameter. And that parameter is the one which is a symmetry transformation, and that point is the one in which you take parameter to infinity. So because of that, it's not among the physically acceptable transformations. But thank you for that question.
And other very simple questions, also very technical, because if you look for your action as R minus R bar, then this is the difference between two terms. One, we know when we go to Euclidean version, one gives us a positive Hamiltonian. The second one, just with opposite sign, could give us negative defined Hamiltonian. What do you think?
Oh, that aspect is precisely helped by the fact that M bar is a lot smaller than M. You are exactly right that I can certainly pick up field configuration if I look here on this slide, which is equivalent, right? So here is M squared, and then there is minus phi squared times R. So let me pick phi to be a constant. So this term is irrelevant. And then this term has minus sign. So it will be giving negative contribution to the Hamiltonian, as you pointed out. But as long as M bar is less than M squared, so overall still will be positive. And it's made out of the same field. I don't have to be imposing conditions on the fields themselves.
Okay, thank you. If there is no more questions, maybe I will ask more general questions. What happens if you try to incorporate supersymmetry? If you go for Sugra, for example, what do you think? Because sometimes when you deal with supersymmetry, it is more simple to treat anomalies or something like this. Do you expect that consideration of supergravity can provide some interesting feature or simplify something? What's your feeling?
Yes, that's definitely a very interesting direction to pursue. I would expect not too much radical surprises, to tell the truth. The reason why is because in this way, when it's written in the Einstein frame, this is just the scalar tensor gravity, and for sure, there are supergravities in which there is a dilaton, and there could be an axion. So supersymmetrization, naively looking at this, I would say shouldn't be such a huge problem. That's what I would think. Although obviously I have not done this, but just that aspect gives me hope, and I think it's a very interesting thing to do. And I apologize, before I switch to something else, I think Michelle was asking for a reference, and then I lost that question somewhere in the chat. So the reference is on the archive. If you go to archive under my name, there is the latest paper or preprint that's on the archive is essentially what I just described to you, with all the comments that I was making. They are there.
Okay, thank you. I see one more question from Alexander from Wigman. Sasha, please.
Giga, last question, probably very stupid one. Can one also think about this theory in the following terms, that we, from quantum field theory, we get this anomaly, And then if you want to cancel this anomaly, we could add this sigma field with this action with minus sign, with the same coefficients which would know about all matter in the universe, and that would cancel the anomaly in that sense. Can one think in these terms about that?
You see, if the scalar field, it won't cancel these coefficients, this A and C. You need to add something more exotic. In fact, Zeitlin and Fradkin and Zeitlin, they do have those representations which do that. But the scalar field won't do the job. So scalar field enhances, it contributes. At least to some of them, it enhances. I cannot remember now the details. So it won't.
No, but what I meant is something even more stupid. In a sense, you cannot get without the sigma field, you cannot get these terms in the trace part of the equations, right? But now suppose you think differently. You say, okay, this is quantum stuff, which basically originates from the point that you cannot take trace and expectation value. But now you add this action with minus sign, right? I mean, it's action for sigma.
Yeah.
And then you generate these terms with just minus sign, and then they will cancel.
I wouldn't call it cancellation, because the anomaly is still there. And moreover, the Rieger term is still there. I haven't canceled it. And there is a very clear signature of that Rieger term, because it makes things strongly coupled at the scale m bar. So it's not cancelled, it's there. And this logic is consistent with what I said before. If you were just to add scalars, that won't help you canceling the trace anomaly. So
okay, thanks.
Okay, I see one more question from Bob Holden. Bob, please ask your question.
Just wonder if you could compare your approach to that of Mottola and collaborators.
Yes. So I would call that approach, well, with all due respect, obviously, with Emil and Ignatius, I'm aware of those papers. Rieger already had that approach in his original paper. So what he did is that he looked at this action that do you see my
yes.
So he took this action, and then he regarded it as I was saying, non-covariant. And because of that, he decided to solve for sigma in terms of the metric G using some special four derivative operator. He used the property of certain four-dimensional operator, certain conformal property of that four-dimensional operator to solve for sigma in terms of G. It's a little technical, but I can actually, if you like, I can show you on the screen his paper, but it's a little technical. Essence is that he expressed sigma through using the Green's function for four derivative operator, and then plugged it back into this action. So as a result, he gets an action which is non-local and entirely written in terms of metric G. But and then he took that action and integrated in yet another field, which removes that four derivative Green's function, but converts it into the propagator of that yet another field. Let's call it zeta, right? So now you have a theory in which you have zeta with Laplacian or D'Alembertian square or covariant version of it, we know with some curvatures, times zeta. So that's your kinetic term for zeta. And then local terms written in terms of G and that zeta. You can do that. That's exact mathematical manipulation. That's what Rieger did. And then Mottola and Antoniadis and their collaborators, they've been writing interesting papers with interesting physical aspects, but they are using those kind of actions or their generalizations. I believe all of them have ghosts because precisely of those four derivatives in the action. So there is no escape from that. That's my comment on it. And it's very easy to see. So on any weakly coupled background, any background you can take, you take a background of the planet Earth. In that background, that theory has a ghost. And that ghost comes in precisely because of that manipulation of solving sigma in terms of G. In fact, you can write toy models. I mean, I've done this. You can write toy models which are absolutely healthy and consistent and simple, and then do kind of replacement of that scalar sigma or any scalar sigma through that kind of Green's function, fourth order operator Green's function. You will start with a healthy theory and end up in a theory which has a ghost.
Okay, I just seem to remember they end up with an action that looks like the action you end up with a simple two derivative term as well.
No, really, it has four derivative.
Well,
it has D'Alembertian squared. We can. I don't have those papers downloaded here, but we can definitely look at it. The key. Well, actually, I can show you that. Just give me a second, because Rigert already has that.
Well, maybe Rigert is much more complicated.
It's a simplified version of Rigert, actually, what they have. What they have is that to Rigert's action, they add the box R, the R squared term in a way that you, in the trace anomaly equation, you have box R, but they chose special coefficient in front of that term, which you can do because it's arbitrary anyway. And that special coefficient simplifies things, but you still have ghosts in that theory. There is no escape from that. That's, yeah, I tried hard to tell the truth, but so it's somewhere here. Do you see this?
Actually, we still see your slides.
I see. How do I do this? View. Do you see this now?
No, yes, yeah.
Yes. Please shift a little bit.
Okay, so this is a Rigert's paper, and this is the action that I was referring to. This is one part, and this is the other one. The action that I quoted is this in different notations. But then he precisely goes here after 14. He establishes the existence of this operator, which he calls delta. This is not Laplacian. This is fourth order operator. Here is a covariant derivative to fourth power. But it has nice properties under conformal transformation, such as this. It's invariant when you multiply by square root of G. And then he uses this property, 12, to express sigma from here in terms of G, and then stuff that doesn't depend on G. And that's done in this formula, in 19. You see, in 19, sigma equals to Green's function of that fourth order operator times this legitimate thing, which is just, invariance in terms of G, plus terms that you can ignore, which are local terms. So, and then he plugs that back into the action and gets non-local action. And then he goes on and says, well, that non-local, I can still make local by integrating in some other field, zeta, and here it is. So that zeta is in this equation, but it necessarily has, as you see, it has fourth derivative.
Okay, you mean forward derivative in the kinetic term?
Yes.
Okay, okay, I see that then. So that's why they have a ghost.
That's why they have a ghost. When it's just fourth derivative, it's kind of singular point, but introduce any weak background and it resolves into two propagators. One is normal, another one is ghost. So always. Yeah, that's a problem, I think.
Okay.
But they did discuss lots of interesting physics, and for sure they emphasized that this sigma is due to anomaly, this sigma acquires some dynamics, and which is true, but it is also true in the Rigert's case. So
Okay. Any questions? If not,
Irina, may I ask the last one?
okay, please.
If Greg permits. Sorry, I just see it's very interesting for me. But last question. So this action is practically would create shift invariant equations of motion, right? I mean shifts of sigma. If you look at the last action, because it's linearly coupled to Gauss-Bonnet, if you forget the coupling to Weil, it's just linearly coupled to basically shift symmetric, right? It's only derivative action.
Do you mean the Riget action? Yes.
Yeah.
This one. This
Right,
one.
this one. Yeah, this
Yeah,
one.
for sure.
Yeah, then it implies that there is a neutral charge, right? Which is
Yes.
and
Yes.
it's kind of non-trivial neutral charge, which involves also kind of curvature terms. That implies that in cosmology there will be non-trivial, as a result of inflation, there will be non-trivial configuration of the sigma immediately, which corresponds to zero charge. This guy.
Well, so somewhat in some approximation, because these things are not invariant under shift of sigma, as you can see. Shift of sigma rescales this M bar. As long as you do two things together, then yes, you have what you just said. And those currents will be generalizations of similar currents that you get for Galileons, except now they are covariantized. Indeed. And then you will go into those arguments that you were just making and people have made in the context of Galileons. These are very interesting, definitely. You will have sectors, super selection sectors. Potentially, I think that's what you were aiming at.
Yeah, even simpler, just inflation kills any charge because charges will be diluted as 1 over a cube. And then you would stay in the configurations of zero charge or zero charge density. And these configurations involve curvature. So it's kind of non-trivial.
Yeah, it can have interesting consequences, definitely, for cosmology, yes. Yeah, this is, you are asking interesting and important questions which have not been looked at because this is 3 weeks old.
Yeah, it's brand new, I know. I know, great, congrats, it's very interesting stuff. Then great to see you.
Okay. So, Sasha, are you happy with the answer or you have more questions?
Oh, I'm very happy with the answer. Look,
Okay.
If we continue, I think maybe I don't have more questions.
Okay. In any case,
write to Greg later.
we had many questions today. Let's thank Greg once again for his very interesting and I would say provocative talk. Thank you very much.
Thank you very much, Gregory.
Thank you all.
Please
for
don't
listening.
forget to
Thank you very
send
much.
us your transparencies.
Sure, I will send you. I will
Okay.
send it to Luca, and he will
Okay.
have
Okay.
it maybe in
Thank you.
a couple of hours.
Okay.
Okay.
So very good to see
Bye-bye.
you all, and so all the best.
All the best.
Thank you very much. Bye-bye.
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 All the
Bye-bye.
best.